I hope they see this camera. So let me introduce to friends of Robotika.SK, Bernd Hader and Felix Sturzl from Technische Universität Wien. And they will present us a robot that we can show you later during the presentation. That's UR5, and that's industrial robot. And we are happy that we can see presentation of our colleagues from Vienna. So please start.
Okay. Okay, so hello and welcome everybody to the DCOT workshop. So we will clarify soon what DCOT stands for and what you will learn today. But first of all, we will start with a short introduction. So yeah, my name is Bernd Hader. So I live in Austria, so I live near Vienna. And yeah, initially I worked as a software developer, so focusing on web technologies. Then I started to study business informatics, and during my study I attended lots of courses in the direction of industrial robots and cobots and things like that, and I found this topic very interesting, and so I also wrote my master thesis in this field. And so the topic of my master thesis was the intuitive programming of collaborative human-robot processes, and the idea was to develop a system which is quite easy for non-experts so that they can program collaborative human-robot processes. And yeah, so I liked this research field, and so I started at the beginning of the year to work as a researcher at the Technical University of Vienna. And yeah, so in April I also started with my PhD, and yeah, also the focus is here on the human-machine interaction and also on focusing on things like safety and security aspects.
Hello as well, I'm Felix Sturzl. I'm at the end of my bachelor in mechanical engineering and economics. I started at the human-robot interaction department in June this year, and there I'm a student employee and I'm working on cobots and other technology. And let's see what we present today for you.
Okay, so let's start. So we have prepared a short video so to introduce you to the topic of DCOT, so into the project DCOT.
In this video, the EIT manufacturing activity DCOT is presented. The activity DCOT aims at democratizing cobot technology. COBOT stands for Industrial Collaborative Robotic Arms. In comparison to industrial robots, cobots are smaller, safer, cheaper, and can be used more flexibly. But what does democratizing cobot technology exactly mean? Democratizing is not the same as a democracy. To understand the meaning and what we are trying to achieve with this activity, we will have to give you a metaphorical example. What is the difference between the computer of the Apollo 11 and an everyday computer? The computational power of today's computers is actually way higher than Apollo 11's. Even though the computational power was not that high, Apollo 11 successfully landed on the moon.
4 forward, drift into the right a little. 30-second forward. Contact light. Okay, engine stop. Tranquility base here. The Eagle has landed.
Since the moon landing, a lot has changed, and Neil Armstrong wasn't wrong when he said,
"One small step for man, one giant leap for mankind."
Computers have graphic operating systems such as an intuitive user interface. We use them each and every day in so many different variations. Windows, the Macintosh operating system, also known as Apple, Android, or Linux, just to name a few. Since then, they have been easy to use for everyone. So, computers were democratized by intuitive user interfaces. Within the context of cobots, this means that the goals of democratization are to achieve a programmable, easy to access, and easy to use cobot for everyone. In order to accomplish this, cobots require that they be designed for everybody. Although there is a simple, intuitive user interface, training is still needed in order little workshop in order to shrink the gap between the public and cobot technology. So-called digital learning nuggets were developed. Learning nuggets are brief digital learning entities that can be consumed on a designated website called skills.move. The learning content developed within DCOT was developed by an international team consisting of the TU Wien, the Technical University of Vilnius, the University of Patras, and the Engineering and Technology Industries Association of Lithuania, LINPRA. We hope this learning path gives you more insight into this topic and wish you a successful learning journey.
Okay, so thank you. So in the video you have seen so that the project name, the DCOT, stands for Democratizing Cobot Technology, and so our goal is, so with the workshops, to spread the knowledge of cobot technology to the public. So we will get more in detail. So now we will have a look and so what are collaborative robots?
You might already know about robots and their industrial application. In this nugget, we will shed light on collaborative robots, also known as cobots. We will see how they differ from robots in general, and finally, we will talk about specific characteristics of collaboration, their common use cases, and how collaboration is defined. But first, let us start with a quick repetition on industrial robots and their definition. An industrial robot is a programmable manipulator designed to move material through multidimensional motions for performance of tasks. Usually, however, as you can see in this picture, robots are separated from humans by protective fences, as serious hazards can occur.
Okay, so yeah, we have now here seen the definition and heard the definition of what an industrial robot is. So yeah, it's a programmable manipulator, and yeah, the problem so with classical industrial robots is that so you need additional safety measures. So for example, fences, and usually the industrial robot you have a cell, and the human cannot get into this cell easily. And so compared to that, we will now look at the collaborative robots.
A collaborative robot, on the other hand, is designed to assist human beings by working in close proximity, where human safety is always the first priority. This distinction leads to essential differences to industrial robots. An application scenario with collaborative robots no longer requires a protective fence, and thus, the space required in the factory is smaller. To ensure assistance, these robots are generally easier to operate and more cost-effective. This is based from the fact that cobots are not and should not work as fast and powerful as their counterparts.
Okay, yeah, so compared to the classical industrial robots, so on the picture, for example, you can see the cobot Panda by Franka Emika. So the company is based in Munich, and so compared to the classical industrial robots, cobots are small and cheap, and yeah, so they have additional sensors so that they can detect collisions, and so we do not need safety fences.
The special feature of collaborative robots is that cobots can work in close proximity with humans. This presupposes that robots cannot cause injuries to humans. With the help of their sensors, they can prevent human employees getting injured or fulfill mandatory precautions for collaborative work. The video shows a typical work distribution between a cobot and a human. And if the human gets too close to the robot or touches it, the cobot automatically switches to a safe state.
Yeah, so as we have seen here in the video, so this was a use case which we have implemented in the pilot factory of the Technical University of Vienna, and so it's a scenario from Siemens, so for the assembly of a heatsink, and so the idea here is so that the cobot is used to transport the transistors to the mounting station, and then the employee is doing the screwing part.
But why does the assistance of a cobot make sense at all? Cobots, just like industrial robots in general, have several characteristics that humans do not have in such a magnitude, such as strength, precision, and them never getting tired of repetitive work. Humans, on the other hand, have superior intelligence, flexibility, and creativity. When combining these advantages, a cobot workplace improves productivity, safety, and quality. This is especially advantageous in small-scale production, which needs to be lean, adaptable to unique customer requirements, and ever-changing product ranges. Furthermore, a cobot can help humans to perform a task and reduce ergonomic concerns due to physical as well as cognitive loading at the workplace.
Okay, so the main thing here is, so as already the headline says, so with cobot, so with cobot technology, the idea is to combine the advantages of the humans and the robot, and so to create processes with a higher quality, so and make the processes better, so with a better ergonomy for the employees, for example.
However, how closely human and cobot can actually work together in a collaborative robot operation depends on the application. There are 4 levels of collaboration. Coexistence. Human and fenceless robot work in adjacent areas but do not have a common workspace. Synchronous. Human and robot have the same workspace, but the workflow does only allow one of them to be within the workspace at a time. Cooperation. In cooperation, a human and a robot share a workspace, but work at different parts. Collaboration. Collaboration describes the closest form of cooperation. Human and cobot have a common workspace and work on the same part at the same time.
Okay, so we have now seen the 4 types of collaboration. So why is this of interest? So because it depends. So which collaboration type you use, you have to think about different safety measures. So for example, when you use a cobot in a coexistence scenario, then the human and the robot, they have their own workspace, and so for example the robot can do his tasks faster. So when you have a real collaboration scenario, so then you have to think about safety measures to ensure that no human is injured. Okay, to sum this up, so we have learned now so that the cobot stands for collaborative robot, and the main point is so that with cobot technology, the advantages of robots and humans should be combined, and there are 4 different levels of collaboration. So there is the coexistence, the synchronous type, then the cooperation, and then the most complex one, so there is the real collaboration where the human and the robot share the workspace and they work on the same part.
So when working with robots, there always have to be some safety instructions, and we will go on then to show you what measurements you have to take to have a safe environment and no accidents can happen. So after this nugget, you will know what is a cobot. We sum this up quite briefly. What are the different forms of collision and interaction? Which physical units play an important role in that? And which safety measures are needed when working with a cobot? So as we have seen before, the definition of a cobot is a collaborative robot, so it's supposed to work with a human. Therefore, it should have a predefined workspace and is a bit slower than industrial robot, so it can't hurt the human. The difference to an industrial robot is that the industrial robot is designed to not work with the human. We have fences around it and safety measures, so the human can't work in coexistence with the industrial robot. So there are 4 types of collaborative operating modes according to the standard ISO TS 15066. That's safety rated monitored stop, hand guiding, speed and separation monitoring, and power and force limiting. And we will go into further detail under those 4 topics now. So the safety rated monitored stop, which will be presented in this video, as you can see, the yellow line on the floor represents the area where the human shouldn't go, and as soon as he enters the area, the cobot will stop working by itself. This works via video sensors. Regarding the hand guiding, there are 2 forms of hand guiding. One form of hand guiding we will see on the left side. As long as you push the button, the cobot will work, and as soon as you will let go of the button, the cobot will not work anymore. So if there's an accident happening or something that shouldn't happen, you just release the button and it stops. On the other hand, there's literally hand guiding, so you can press a button and move the cobot quite literally, and we can show you that afterwards on the cobot itself. So let's come to the third one. It's speed and separation monitoring. As we've seen in the video before, the cobot knows when someone is entering, and if you get closer to it, it moves slower till a point where you're too close to it, then it won't move anymore, and therefore it can work on its own and knows when a dangerous situation is coming up. Let's get over to the last, monitoring. It's power and force limiting. As you can see, depending on the cobot and on the motor, they're quite sensitive, so it only needs the touch of a little finger to activate the brakes and stop. Afterwards you have to release the brakes manually, so there can't be any collisions that are frightful for the human being. So there are actually 2 types of collisions, quasi-static types and transient types. To go over it in short, quasi-static means that your hand, for example, and the robot is captured between the robot arm and the table, and there's constant pressure on it, which the robot applies on your arm. The other accident or collision type is transient, so if the robot arm moves around in the room and it hits you on the head or something like that, this will cause serious injuries depending on the speed. So safety measurements are very important, so no one gets hurt. Therefore, physical parameters are set. The speed should be low and not too fast, because if the robot arm is moving way faster, the accident will be greater, and therefore the amount of injury to the human will be more. Also, the force is important. If you have force sensors which are quite sensitive, they will stop in time. If they are not sensitive enough, they probably will hurt you and won't stop in time. Now we have a video which sums up what I've told you. So keep watching and enjoy.
Check. Checkmate.
There was a breakthrough in robot technology. Welcome to the breaking news. A VW worker was killed by a robot.
Emergency service was called.
But the 21-year-old died in the hospital.
Welcome to the safety instructions. Cobots always have a certain reachability of the robotic arm. This has to be considered when working near or with the cobot. There are 4 different forms of operating a robot. The most common one for a cobot is the force and power limitation. A CE certificate on a cobot does not mean that the application with it is safe, since cobots are incomplete machines. The whole cobotic setup, with all its components, is relevant for safety assessment and certification. Thus, a risk assessment is needed. It is recommended to do one in cooperation with a third-party company, like TÜV. For more information on safety, please refer to the following engineering standards. In order to demonstrate the safety measurements, we will now present 4 different ways of how to be a bad loser.
Ha ha, you idiot. I win. You lose. Checkmate.
In case of emergency, please immediately press the emergency button.
Ha ha, easy game, I win.
No, not this time.
What are you doing?
Never place body parts between the robotic arm or its end effector and stationary objects.
Checkmate. Hey, this is cheating. Put it back.
Never put any body parts between the end effector fingers.
Or next time I will crush your fingers.
Do not wear accessories or anything that can get entangled by the cobot.
What is your problem? Come here, I'll kick your ass.
Also, if you have long hair, please tie it up. Please always consider that the robot and its setup parts may pose potential danger. Always keep sufficient distance and do not handle the danger recklessly.
So that's it for the safety instructions, and now we go back to slides.
Okay, so now there will be a short introduction to universal robots. So we have already heard that the cobot is a reprogrammable machine. So Universal Robots is the market-leading company on the cobot technology market. And yeah, we have also already heard so that the main purpose is to support the humans. So the universal robot, so when you buy one, so it usually consists of 5 components. So first there is the robotic arm, so it's this one, so you can also see on the live stream camera a universal robot, so the UR5. Then, so you will need a specific tool. So for example, here we have a 2-finger gripper, but yeah, you could also mount, for example, a screwdriver. Then we need so a tool for programming the cobot, and so here we have the so-called teaching pendant, so it's a tablet and you can interact via touchscreen. Yeah, so finally you also have a user manual, so I think it has 200 or 300 pages and is very detailed. And so there is also a control box, so as you can see in the picture at the bottom left. So the control box is then the brain of the robot, so where the robotic arm and the user interface, so the teaching pendant, the tablet, they are connected. So and when you buy a universal robot, so then you will get the arm, the teaching pendant, the user manual, and the control box. And yeah, depending on the specific use case, you have to buy the specific grippers, for example, the 2-finger gripper. So let's look at different components a little bit more in detail. Okay, so the arm is the main moving part of the universal robot, and as you can see here on the picture, so on the red lines indicate the 6 joints. So this means so you can move the robot arm by the use of these 6 joints. Okay, so then the tools, as already mentioned, so there are different companies providing different tools. So for example, here on this picture, you can see the screwdriver mounting, or then we also have a vacuum gripper, and also 2 other examples of other grippers from the Technical University of Vienna or from the LMS Patras. Yeah, so then the teaching pendant, so this is used for programming and controlling the robotic arm, and so it consists, so there are only 3 buttons. So first of all, the most important button is the red one here, so it's the emergency stop, so if there is any problem or something like that, so then you can press this button and the robot will stop immediately. Yeah, the second one, yeah, you can power on and off the robot with this button. And finally, so we will see this then live. So there is a 3rd button at the back, and when you press this button, then you can move the robotic arm, so with the free drive mode, so manually by hand. Yeah, okay, so the user manual, I think this should be quite clear. And then we also have this control box, so you can see how it looks like inside. So here you have also the possibility to add or to connect additional sensors or additional buttons, yeah, depending on your specific needs. Yeah, so then let's have a short look at some important or interesting technical specifications. So as you can see here, so first of all, so there are 4 different types from the universal robots. So there is the UR3E, the 5, the 10, the 60. And yeah, one important thing is the reachability. So the UR3 has the smallest one, so only 500 millimeters. The UR10 has the highest with 1 meter and 30 centimeters. So then the payload, so the payload is the maximum weight so that you can transport with the UR arm. And yeah, so it's important that it's a limitation of the arm and not the tool. So what does this mean? So for example, the UR3 has a payload of 3 kilograms, and this means, so you have to think about of, you have to sum up so the weight of the tool and the transported good. So for example, if you have attached a heavy gripper, so for example with 1 kilogram, so this means when you use the UR5, then you can only transport goods with a maximum of 4 kilograms. So you have to keep this in mind. And yeah, so here you can see why they have chosen this naming convention. So with the UR3, you have a payload of 3 kilograms, and with the UR16, so it's the big brother or sister, and so you have a payload of 16 kilograms. Yeah, so then the total weight in the base diameter, so yeah, this is only so to know a little bit about so how about the weight of the cobot. So the UR3 has about 11 kilos, the UR16, so the big one, has 33, and here the base diameter for the mounting. And finally, so this is also very important, so the pose repeatability. So, and this defines the accuracy of the cobot arm. So as you can see here, so the pose repeatability is quite small. So for example, for the UR3 and UR5, there is 0.03 millimeters, but you have to keep that in mind. So if you have a specific use case where the parts and the different assembly tasks have to be very accurate, so then you have to think about that before you buy a specific cobot. Okay, so and then only to get a feeling, so how can we program such a cobot? So we have here a picture, so here is the teaching pendant. When you start the cobot, then this screen will appear, and yeah, the way to program the universal robot with the teaching pendant, so is called, so the program is called Polyscope, and yeah, so I think we can skip, oh yeah, okay, we can have a short look. So there are different possibilities, so you can run an existing program, or so you can program the robot and things like that. So I think we can skip this. So only to get a little feeling. So when you program the cobot, then you will see this interface, and so the program here you have, there is a, so it's a tree structure, and at the left, so here you have the different commands. So for example, if you want to move the robotic arm from one position to another, then you will use the move command. Then you can define the waypoint, and so then the user interface will look like this. So you have the 3D presentation of the robotic arm, and then you can move the arm simply by pushing the different arrows. Yeah, I think that's enough for the programming part.
So we designed together with the other universities a use case where a collaborative robot could be used. Just a minute. Program is crashing on us.
Maybe so far I can show. Okay, thank you.
So how can a cobot help with production? Like we said before, it can be used for many different tasks, like welding, screwing, pick and placing, and assembly. And it helps workers with monotonous and unergonomic tasks, so workers can concentrate on core competencies or work that a robot cannot do. It's also very versatile. You can program it to do many different things. So if one task isn't used anymore, you can program it for a different task to use, unlike industrial robots, which are designed to do one thing only. So this is a cobot work area we use in Vienna. We have the cobot, a gripper, the teaching pendant, and an assembly station with fixtures. These fixtures are used to handle different parts. In this case, the thermostat contains of 3 different parts. So it's the main body, the back cover, and the PCB board. And normally, this work is done by a human by putting the parts together. You have to be quite careful because the PCB board has very long pins, and this is a process which will take place 120,000 times a year. So it's a task you could easily replace by using a cobot. So why do we have fixtures? You have to have the parts precisely at the same position every time, so the cobot can pick it up every time, and therefore you need these mountings. As a gripper, we are using a 2-finger gripper today, but in Vienna we also have a pneumatic gripper which works with pressure. So normally the worker takes the sticker, puts it on the front part, then the label, puts it on the back part, and has to put the 3 things together. And now we found a way where the human can take one place of the work and puts on the stickers, while the robot can put together the thermostat. So let's see how that's done.
The Robotic project has as goal to design a workshop where human-robot collaboration technology is going to be introduced to non-experts of the field. One of the workshop's parts is a demonstrator where the operator collaborates with a robot to perform an assembly. The project is conducted in collaboration with TU Wien, Limra, and Vilnius. The ATEX use case involves the assembly of a thermostat. It is suitable for the demonstrator as the process involves small parts assembly and small forces, and therefore it can be transferred easily. The procedure begins when the operator presses the start-stop button and then sticks the stickers to the parts. First, he sticks the body sticker to the body part, and then the label to the bottom part. During those human operations, the robot assembles the parts that are placed on the fixtures. When there are no parts left in the fixtures, the operator places the new parts in the fixtures. First, places the bottom part, then the body part, and finally places the PCB. When all parts are placed, the robot begins the assembly procedure.
Okay, and now we will show you in person how it's done. So, as you have seen in the democratizing, it's very easy to program a universal robot. You see that like that? You just have a structure and you set waypoints and it goes directly from one waypoint to another. Then you have also commands for gripper opening and closing. You can do linear movement, so it's especially straight and not the easiest way for the robot to move. And you also have like wait commands. Further on, you have advanced commands for looping and if-else routes. So there are ways to program it even more detailed. But the core instructions can be learned in about an hour. You take 10 minutes to get used to it, and then you will get a feel and hang of it. So I've worked quite a bit now with this robot, so I could program this task in about 20 minutes, I guess. Start it.
You can switch off microphone. You have the microphone, and I will switch mine.
While the cobot is doing this, I could be able to put on stickers and label on the top and bottom of this, and therefore it's a shared collaborative work. And you only have to take 20 or 30 minutes for an experienced worker to program this. So it's mostly used for small and medium-sized batches, while the human can do some other work. Just to show you, you can set the waypoint quite easily with the arrows like we talked before. You press the up button, it moves up. I hope you can see it. Also left, right, and the rotational work. Okay. Okay, so you have different arrows. Move it, you can set the speed as well, and also open and close the gripper. And like we talked before, we also have manual mode. Yes, sir. You press the button, please. If you press the button on the back of it, I can then take the cobot and move it with my own hands where I want it to be, and take the place in the part right side. So that's it, I think, for the collaborative robot. So if you have any more questions.
Yes, we have some questions from chat.
Yeah.
One question is what about the cobot operating system? Is there any industry standard operating system?
So Universal Robot has this Polyscope program to write this. You can actually download it and program it on your laptop as well, and then transfer it to Teaching Pendant. Since the program is so simple to use and democratized, there's no there's not any previous programming knowledge that you have to have.
Okay, so to add only a brief comment, so no, there is no standard, so each manufacturer usually has its own programming operating system, so like Universal Robot has its own, or ABB has its own, but there are also projects like ROS, so the Robot Operating System, so it's open source and free, and can and could be also used, for example, for programming the UR5.
Okay, but robot operating system is available for Linux and not for Windows, for instance. So it means that the user is limited in the platform.
Yeah.
Okay. Any other questions? Have you some questions? You can also.
No, everything's understandable and very nice.
Okay, and would you like to play with it, or you can show something to people who are here, that they try to do something by them?
So we can make one of these.
You can join. Just stand from the other side to enable camera to work.
It's just one new program. So here we have the different parts. Let's take just one because we don't want to be here like 2 hours, I guess. First, you have to set the waypoint where you start. Super easy. Look at this. Maybe you should change position here. So you have information and just set a new waypoint. Then you have first on the waypoint. To set it, but the person will set waypoint. So we don't do this right now because it's only for rotation. But up, down, left, right. But I think for a start, this is a good starting point because we're on top of it. We can't get a collision with anything. So we just press OK and get to the next waypoint. Okay, so we want to add another waypoint. And now set it again. And the next thing we want to do is to pick up this part. So, like we said before, it moves in a direct way. So, where do you think does the next waypoint need to be?
From this here.
Exactly, we have to be above it. Because if you go in a direct way, there could be a possibility that the gripper touches this cube and then it will get stuck. So we have to move to the left now. But it should be very precise because afterwards we go down. How should we do that? Pretty hard to do. So what I would suggest is we go down here and try to get this point first, and then afterwards we introduce the other point.
Okay, so we move down, right?
We just move there and let's try to grip it, therefore it has to be right-centered.
Okay, so we don't move left after we move down, right? So first of all, we will move down and then left.
When we have the program, we move left and then down, but the program doesn't recognize how you got there. It only knows waypoints to waypoints. So we just get to try to get to waypoint 3, because we have to be precise here. And afterwards, we just implement waypoint 2. Okay, so we just skip it for now and do waypoint 3 now.
Okay, so go down, right?
Down, left, 1, 2. We have to get more in this direction, I guess. Want to go slow, you can change the speed. That's really slow. Okay, we just give it press.
You just need to set each point personally, right?
Yeah. Or with the manual mode. But the manual mode, like I showed you before, works way better with things that aren't so tiny and don't need that much precision. But because the parts only get fixed in one way, you need to be pretty precise. So I think we need to go farther down because we want to set the point that really grips it. A bit more in this direction as well. A bit lower. That could work. So let's set the waypoint. And now we just try if we're really gripping. Therefore, we can open this one. This is the UR caps, like an app. And now you can open it again, probably. I think we were a bit too low.
Okay.
So we set the waypoint again and go just a tiny bit up. So if we press the button on the right here, it closes the touch section. Have you seen the problem? Open it again. And if you close it and watch closely, you see that it touches the left side way earlier than the right side.
Mm-hmm.
So we have to change our position to the left side now.
So our waypoints must be pretty precious as well.
Yeah. Therefore, a good suggestion was for a cursor like this to put the laser pointer on it, so you already know where it's pointing it to get the middle easier. Pretty good. And now we set to waypoint 3. Just go. So just straight up. Okay. So now we went from this place to this place to this place, but we need this place as well in front of waypoint 2. Okay. So we need to copy it. Therefore, we have here the copy command. Then we go which point we want to set it in and can paste it with the one on the right. Okay. Okay, so now we go waypoint 1, waypoint 3, waypoint 2, waypoint 3, but we need to set the grouping part as well. So we want to group after which waypoint? After second. Indeed. So we go to the UR5 command and go to grouper. And now edit the action. We want it to fully close. 10% is probably sufficient enough. You can disappear. And then the parts as well. Probably also only 10% because the thermostat doesn't have a lot of weight. And then we save the action. Okay. Then we could add on another point to move it around here, but we just do it with the basics again. So the waypoint just around here, we don't have to be super precise. Just so we have to like this. Okay, so press OK. Now we open the grouper manually because we haven't programmed the loop. And now you can take a look what we have done so far. So we move to the initial position by pressing play. Take from beginning. Now you have to keep this button pressed to go to the first waypoint. And then we press play, and when we start a new program, we always keep the safety button closed. Let's just see how it works. Okay, it was a bit of a problem. We weren't precise enough, probably. So we must edit this point again.
So it went to the right.
It's waypoint 2, exactly. And now we can move here. But before that, we open the group again. And move back to this position. So we were probably a bit too elevated this time. We can do it. Set it again.
Great. We have yet another question. I think the answer is clear, but the question is, are you using machine learning here, for example, for object recognition in a robot workspace and finding its bounding box? I think we just employ that the robot has very exact positioning, and he can repeat very precisely what we plan to do.
Yes, of course. So
but can we combine somehow this robotic arm with camera and some processing based on machine learning?
You know exactly on that with machine learning. I just know that
Yeah,
you can add a lot of sensors.
So it's possible to connect the camera and then use different machine learning algorithms. So also at our institute, so some people are working on that topic. So they put a camera on it and then they can use the algorithms and they can detect different objects. Yeah, so that's possible.
You see? This is great. Welcome back. It probably works, right? Now we'll try move up.
Oh.
This time it's working. Okay. So let's try it again. There was a lot of people trying this today. Okay. Let's try to program once more and hopefully it works now.
Yes, working fine.
Actually assembly. So now it works. Okay, and if something would occur because we haven't stopped the loop, we just press the emergency button and it stops, and we have to initialize the robot again manually.
Okay. And can I ask about the version of the robot? Is it a robot for 3 kilo, like with 3 kilos maximum?
This is the robot with 3 kilos maximum. So the tool and what we're moving is maximum 2 kilos.
Yeah.
But we also have like the UR10, which has way more reachability. It's 1.3 meters, so you can reach something that's around here as well.
Yeah, pretty big.
Pretty big, yeah.
Okay, and about the software, was it written by your team or it's like...
The software is done by Universal Robots itself, the company.
Okay.
And I don't know, it's pretty easy to use, I think. After some time, so you get used to it. And it's about this democratizing theme, so it should be accessible and easy to understand for people who are not too much into robotics or programming. And I think that they do it very well.
Not so many experience.
Yeah.
Okay, thank you.
Okay, we have thank you. We have 2 additional questions. One is aimed to the tool of the UR robot. That whether you have tried to solve a Rubik's cube with this robot. I think with this gripper it would be not possible. But have you some tool that could manipulate Rubik's cube, or have you tested this?
So we haven't done it this far. Maybe it works with the fixture and like another cobot. So you have 2 cobots. But I guess
okay.
it's pretty hard to program it. It would take a while. But no, we haven't done it.
Okay. Another question is that are you trying to use such kind of robot for reinforcement learning? On one side, I think the robot has perfect positioning, so it would be potentially working, but that would be rather like test of the robot sustainability, because the reinforcement learning would require too much of movements simply. Typically it is performed in simulators as far as I know, and so I doubt that somebody have used, but if yes, then just tell us.
So we didn't implement this, but there are lots of projects, and also at our institute some colleagues are working on things like that. So we don't have experience with this topic. So
Okay.
sorry.
Yeah,
Maybe so far, yeah.
Yeah, so far.
one more question. You mentioned 2 cobots, so it means that they can work simultaneously in one workspace, and it's pretty okay. So they will work.
If you program them in the right way,
okay.
Of course, but if you let them collide, they would stop. So we also have like wait commands. So one robot could do this movement and then has like a wait command for 10 seconds, and during this phase the other robot could grip it and turn it.
So it's pretty dangerous, but if you are clever and careful enough, it's...
I don't think it's that dangerous, but I can show you. Let's open the group file. If you just start a program and one of the robot arms would hit the other arm, I can show you what would happen.
Okay, yes.
So it probably won't be sufficient, but it has force sensors, and if the force gets too strong, so one arm touching the other, it will stop, and you have to manually enable the robot again to move.
Okay, yes, I see.
Okay, so I think no more questions, so thank you very much for the presentation. And the other questions can be put personally later, but we can stop recording. And thank you everybody for joining us today. I hope you have seen interesting machine, and hopefully we will touch also this machine one day in our laboratory Fab Lab. So thank you so much and goodbye.